Hello everybody, this is lecture 8 of the course Signals and Systems by Mr. Amr Abdul Bari, Department of Electrical and Electronic Engineering, Nearest University. Today I will continue in the Fourier transform and Fourier series. To remember, we uh, we use time domain as s of t. This is a time domain for the signal. We use the Fourier series or Fourier transformation to find the frequency domain. What is the frequency inside the signal, inside my signal? So we find that there is, according to the property of the signal, which may be periodic or non-periodic, or which may be continuous or discrete time signal. So here, if it is periodic, we have Fourier series for continuous and discrete time. For the discrete time Fourier series. For non-periodic, we have Fourier transformation and the discrete version of the Fourier transformation. Today we will see the Fourier transformation and the discrete time Fourier transformation or transform. Beginning with the discrete time, let's see that we have a non-periodic signal, so we don't have a fundamental period and or a fundamental frequency. So we will describe the signal as we will describe the signal if we have the signal x of n, to find the x of n from the frequency domain. We will have the frequency domain multiplied by the e to the power j omega n. Okay, so we don't have omega 0 here, and this is integration 1 over 2 pi. Okay, x of ej omega, we have it in a summation. If I have the time domain and I want to get the frequency domain, so it is summation from minus infinity to the infinity, multiplied again by the minus of the power, the same power here, but it's in minus. So the again it's the same as in Fourier series. In Fourier transform, it is reversible. So if you have the time domain, you can get the frequency domain. If you have the frequency domain, you can return back and have the time domain using the discrete time Fourier transform and the inverse discrete time Fourier transform. Okay, now let's see some examples. And if he gives you here the signal, it is alpha to the power n multiplied by u of n. So I will use this equation to get the frequency domain. He said find the discrete time Fourier transform. So if he gives you x of n, you will find x of e to the power j omega. Now after writing the signal, you will just remove the x of n and put whatever is here. So u of n, you can remove u of n and begin from 0. So it's easy, from 0 to the infinity, and multiply to alpha n. Here alpha, if it is higher than 1, then it will diverge. Then I can't find the summation here, a solution for this summation. Okay, if it is less than 1, then there is a solution that we see it before. You can take the n from outside 1 over minus whatever is here. Okay, this is for alpha less than 1. Okay, so if it is real, if it is alpha is real value, then we can this value we can expand it. E to the power j omega, it's equal to cosine omega plus j sine omega, and the alpha will be multiplied in the both of them, minus here. Okay, so minus is positive. This form, you can find the magnitude and the phase, so you can draw it at the magnitude and phase of the non-periodic signal. Okay, the frequency components and the phase of these frequency components. Okay, Now let's see the inverse. We have here in the book this example of he said he gives you this in the equation head, and he asks you to find the inverse discrete time Fourier transform. And this is the equation one wherever minus w to w and 0 otherwise. So to find that, we will use this equation. We will write this equation, and we will put 1 from w to w, it is summation. So from minus w to w it is 1, and otherwise it is 0. So the equation is from minus infinity to infinity, but we don't have anything there, it is 0. So you will take this integration here. Integration is very easy for e to the power j by omega, j by n, sorry. So you will take this in the denominator, and 2 pi from outside. This is integration from minus w to w, then you will have from minus w to w. Now this equation, it's equivalent to the sinc signal. This is using L'Hopital rule. This is sinc. This is another like we said before, that we have a rectangular signal, we have delta signal. So now we have something called a sinc signal. It's sine over the value from inside. So it is sine here. Sinc, it is sine the value wn by over wn by. Okay, so the by is in the sinc, so the sinc is w by multiplied by n, sine over the value inside, whatever it is, wn, whatever it is. This is sine, sorry for the writing, sorry, yes, this is sine over whatever inside, w again n by, so whatever missing you will just divide by. Okay, so here it is missing the by, here missing the w, so here I divide by w, and here divide by omega. Okay, this new function, this is if you put n 1 2 3 4 5 6 and whatever, you will see that the function is like this. It is have a peak, a very big large peak here, and it is smaller until it's converged to 0 in the at infinity, and the same from this side. Okay, now let's see the continuous time non-periodic signal. We use here the Fourier transform. Okay, so we in this side we use t instead of n, so it's almost like the for periodic signal. The only exception is there is no omega 0, there is no fundamental period. Okay, so here you just j omega t, and here j omega t minus again here in the to find the frequency domain. You will see the minus in all of them in the equations. Okay, and again all of the Fourier series and Fourier transformation is reversible. So if you have the time domain, you can get the frequency domain. If you have the frequency domain, you can get the time domain. Okay, now let's see an example. He gives you this signal, we see it before, e to the power minus at, and he asks you to find the Fourier transform for this signal as shown. So you will see that if you find the equation from 0 to, if a is less than 0, from minus, it will converge to 0, infinity, not converge, diverge. so we can find a solution. If it is higher than 0, then we can find a solution. So from higher than 0, so it is 0, from 0 to infinity. Okay, now you will just put in this equation this x of t, you will remove x of t and put e to the power at, okay, e to the power minus at, as in given here, u of t is giving from 0 to infinity, so you will take it from outside, and now you will just solve for this integration again, this simple integration from 0 to infinity. So you will find that this is the output of this integration. This is the frequency components of this signal. So you can easily find the magnitude and the amplitude. Again, the magnitude and the phase. The magnitude is you take the square of the this is the magnitude of, you see here, this is j, so it is a complex number. What is the magnitude of the complex number? It is the summation of the real number square, imaginary number square, under the square root. Okay, and the phase is minus 10 to the power minus 1, the imaginary part over the real part. So you have to revise the complex numbers so you can find the real part and the imaginary part, or the magnitude and the phase of the a complex number, which almost all the most of the frequency domain is a complex number. Now, so you can draw it here. You're just at a, 2a, 3a, you can easily draw it. Now let's see the inverse. The inverse here, find the inverse here again for the rectangular spectrum, 1 from minus w to w, 0 otherwise. I will just use this equation again, this equation. So I will remove this and will just 1 from minus w to w and 0 otherwise. Here he gives you, take the integration again to for e to the power jwt, and you'll find that this is sine wt, or 1 over by t, which can be simplified again to sinc. Okay, sinc, as I said before, it is w by t, 1 over w by t. So we don't have pi here, so I will divide by, and here we don't have w, so we will divide by, it will be in the numerator, so it's like this. So it's this sinc. I show it before the drawing of the sinc. Okay, thank you very much for listening. This is for today.